Well, let's go ahead and move on to the last section. So following the pattern we've been on, it'll be 45 minutes, and then we'll be done. No time for instruction or for the exercises. Although the exercises are available to you, sample solutions are provided. So we're going to do a bit of a whirlwind, quick run through some terminology. If you've been doing parallel programming, this is fairly routine, refresher for you. If you haven't, there's some important terms that get thrown around a lot that we want to make slightly more clear. So parallelism, right, simple idea. And when I say CPU, I mean I'm being very vague and abstract. What is a CPU? Let's not get into that. But serial programming, you have some kind of problem sent to one compute resource, whatever that means. And in parallel programming, you're chopping up the problem and using multiple compute resources, whatever that means. So here's the, it's kind of ugly, but I still like it anyway, diagram that I have. So if we're going to make lunch, right, here's the serial approach, where, you know, you have to wait on this to get this or swap them, whatever, but there's still sort of a, there's a dependency before we can get here. Here, we can chop the problem up, combine, and then we're done, right? So simple idea. Implicit parallelism. So this is parallelism where the details are hidden from the user. Before, when we looked at using open BLAS with two threads, that was implicit parallelism. I was doing matrix factorizations and matrix multiplies in parallel without having to change any of my code, right? I just had to change which BLAS library I was using underneath. Explicit parallelism is, as I say, some assembly required. So when we talk about MCLApply in a moment, that is explicit. Some terms that get thrown around a lot are embarrassingly parallel or loosely coupled. And the idea, as I say, is it's obvious how to make it parallel. There's very little data dependence, or if I back up off the word data, independence. There's lots of independence in computations. So like if you want to fit two independent models in parallel and you're not modifying the data, as the things work in R, then it's trivial, right? It's obvious. You should be embarrassed. It's so easy, right? The opposite of that is tightly coupled, and this word gets thrown around a lot less, but it's still very useful. Tightly coupled problems, that's the opposite of embarrassingly parallel. There's a lot of data, or I keep saying data, there's a lot of dependency, whatever we may be working on. There's a lot of dependency, right? So if you have one model that you want to fit, and it's huge, and you want to make that faster, you want to use multiple compute resources to do that, that's a tightly coupled problem. That's a much harder problem than this for our users. Wall clock time, I think I've even said this word a few times, time of the clock on the wall, right? There are other measures of time, the compute time, which if you're using multiple cores, you know, these things will differ. Speed up, we refer to speed up generally with respect to using one core. So you might say the time for one core versus the time for 4 cores, right? And you would define that as your speed up. And this would be good speed up, where here the blue is a theoretical optimum. It's actually, you can cross over that line. It's possible. But most of the time, if you do really well, it'll look like this, where your program in parallel is dipping under the optimal as you increase the number of cores, your speed up. This would be bad speed up for a certain class of problem. You might want to remeasure things if you are. So here I'm sort of assuming that you're keeping data sizes fixed and throwing more cores at a problem. There's another way to measure performance. We'll get to that in a moment. So shared memory, we're not going to get hardcore into hardware, but in shared memory, it's like your laptop or your desktop, but not 2 desktops or 2 laptops, right? The compute resources have some kind of direct access where they don't have to go over network. In distributed computing, you have to go over some kind of network. Hopefully it's high-performance network, like a server, a supercomputer, cluster computer, whatever. So here are some examples. This is a machine at the University of Tennessee called Nautilus. It has 1,024 shared memory cores and 4 terabytes of RAM. So you can run OpenMP with 1,000 cores on this thing, or MCLApply with 1,000 cores. Kind of neat. Here On the other end of the spectrum is distributed memory machines. This is Titan at Oak Ridge National Lab. And this has hundreds of thousands of cores, almost 300,000 cores. It also has a bunch of GPUs in it that nobody knows how to use. It has 600 terabytes of RAM, right? So to give you some sense of perspective, this is a very large shared memory machine, right? They don't get much bigger than about 4 times the number of cores, as you see here, or maybe slightly bigger now, but last I checked. These things get enormous, right? There's even there's a machine in China that has a bunch of Intel mics in it, and if you count those as normal cores, it has like 3 million cores, maybe. It's something ludicrous. So, so there's a very different scale, right? So if you have an astronomically huge problem, you really have to go distributed. And these are just examples, of course. You know, there's other things that you may be familiar with, like a Hadoop cluster. It's still distributed computing, but is probably less sophisticated in terms of the hardware than a supercomputer. So in R, we have some shared memory utilities. Parallel is sort of the default one that we'll be talking about. Older packages, Snow and Multicore, not there for some reason, which have been basically incorporated into Parallel. ForEach, there's also GPU tools. There's a package I co-developed with Norm Matloff called ARF, which can do some GPU stuff. There's HyplarM, or HyplarM, which can use Magma, which can do matrix factorizations on GPU and brought into R. So these are R packages that I'm naming here. Distributed computing, there's PBDR, which I'm one of the developers of, so I'll probably talk about that a little. There's RMPI, R Hadoop, Repay, although I think R Hadoop has sort of overtaken this one. This is sort of an ecosystem of packages now. Even more things, if you go to the HPC Task View for, this is basically all the parallelism, high-performance computing stuff. This is a slide by my colleague George Oshkov, right over there. And it's a way to try to visually place all of these things together and how they relate to the hardware. So on your shared memory machine, like your like on Nautilus or your laptop or whatever, you have things like OpenMP available, threading and forking through like multi-core parallel, access to threading through OpenMP by going out to, for example, RCPP. There's an example of that in the exercises of this section. Magma, Plasma, these things work on accelerators, coprocessors, like a GPU or a mic. Mic is sort of the x86 version of a GPU, kinda. We have a machine that was mentioned earlier called Beacon, stuffed full of those mics. It's pretty cool. Then ScalaPack, Pblaws, Blacks, these things are for distributed computing, linear algebra. ELIPack and BLAS, we've discussed. These things can, depending on your implementation, can work with an accelerator or not. On the distributed computing space, there's Hadoop, there's the PBD stuff. Snow can kind of work in that space. There's socket computing. There's stuff like MQ, like 0MQ. There's all kinds of stuff, right? Can't talk about all of it. So we're going to talk about some of it. Some basic guidelines. Parallelism requires some form of independence, right? I'm trying to think of the better version. There's a good joke about parallelism. There's a better version than this, but you know, you can't get 9 women together and then have a baby in a month, right? So with parallelism, you need some kind of independence. Does that make sense? Right? Okay. So there's a better version of that joke, and I can't remember. I apologize. But separate evaluations of R functions, with some very minor caveats to that statement, are embarrassingly parallel. Meaning, if I have an R function and I want to operate on different data, I can. It's cheap and easy. And this is where I kept mentioning why thinking in terms of ply functions is valuable. Because changing like 2 letters of a function, we're going to get parallelism working from the ply functions. So it's pretty nice. So an example, you're thinking of fitting a bunch of models independently, you're going to pick the best, and then this is embarrassingly a parallel problem. Many R packages will not work on Windows, or parallel R packages. A lot of the distributed stuff will break or just won't install. In my opinion, like the cornerstone, most useful thing, MCLApply, simply does not work on Windows because it requires forking, and there's no system fork utility on Windows. So if you have a Mac or Linux or BSD or whatever, things are great. But a few things, generally it's going to work everywhere but Windows, may also work on Windows. Random number generation, be very careful, because random number generation is not really random, it's very deterministic, and you probably know all this, but if you're doing any kind of simulation in parallel, you have to make sure you are using a generator that can accommodate that. So there are some packages that make this very easy. Here they are. We won't get into that. It's sort of a separate topic, but those packages work very well. So this is parallel programming in theory, right? In theory, it's like this, where all of the resources are very nicely lined up with the data. In reality, it tends to look a little bit more like this, right? Where it's chaos and madness, and God help us all. That said, I don't want to dissuade you from parallel programming, but when you're learning parallel programming in R, it's very easy to go, oh my goodness, this is so easy. And then once you leave the comfort of R and you're thinking about like distributed programming, or you're thinking about multi-threading, things get ugly in a hurry. Parallelism in R is very, very, very easy though. We don't have anything like the GIL and Python. Like, it's really nice. So many kinds of parallelism available to R. You know, you've got parallel BLAS things to think about. There's all these different packages available to you that solve all of these problems in different ways, depending on what your problem may be. But now we're going to talk about parallel package and the ForEach package. Okay? So the parallel package, as of R 2.14.0, ships with R, and it has these two disjoint interfaces built into it. The older packages Snow and Multicore, parts of Snow were rated, all of Multicore and then some was rated and put into the parallel package. So there are these two interfaces in parallel, and if you don't know the history, you would wonder why on earth they bothered to do things in such a bizarre way. The reason is because it comes from two completely different packages written by completely different people. The multicore side of things, okay, on the multicore side of things, it uses fork. So you got your R session, you fork a bunch of other R sessions, operate on some data, you recombine, and you're done. It's great. Forks tend to be pretty cheap. The operating system is only going to copy data on write. So if you're modifying data, a copy will be produced in the children, but otherwise no copy would be produced. It's not as fast as threading, but it's very fast. You know, if you're working in R, it's quite nice. Okay, so data copied to child on write. This is handled by the operating system. You don't even need to think about that detail. How nice. And it's efficient. It's pretty darn good. No Windows support, as I have mentioned, because it uses a system utility that's not available on Windows. Every POSIX system has it, so Mac, Linux, whatever, BSD, FreeBSD. Not as efficient as threading. Generally, you can do much better by threading, but it's still pretty nice. It's not a huge difference. So here is the function dispatch, right? MCLApply, X function, and then a whole bunch of options. Most of them you can ignore. So I mean, you have options for pre-scheduling, managing seeds. Let's see. So how many cores you want? MC.cores. But otherwise, it basically works like an lapply. So here, if I say lapply 1 to 10 square root, remember what that does. It takes the vector of integers 1 through 10, applies a square root to them, returns it as a list, right? MCLApply does the exact same thing, just using multiple cores. And by default, I think it's going to try to use the number of cores detected by your system. How many that is depends on what kind of hardware you have. Like what are those fake threads called? those fake cores called hyperthreading. So if you have like hyperthreading available, I don't recommend you use hyperthreading with MCLApply, but if it's enabled, it'll try to use them, whatever. And we can see all.equal is just going to test, are these things identical? X.MC and X, and they are. So it does the exact same thing, just using multiple compute resources. In this case, cores on your shared memory, laptop or desktop or whatever. So this is okay. The point of this is, so the simplified to array is basically to make MCLApply look like SApply, because I don't want a huge list in my printing. So just ignore that. Pretend this says like MCSApply. It doesn't exist. I don't know why. 1 to 10, function I, get the PID. So the PID is the process ID. So it's sort of like a fingerprint on your system for the R session, let's say. So I run that with 4 cores, 1 to 10, and I should run unique on it too, but we get 27,452, 53, 54, 55, and then they start repeating, right? So I'm running 4 legitimately different R sessions here. That's what I'm trying to convince you of. And here, if I swap this down to 1 to 2, and I say 4 cores, it's not going to do something stupid. It's only going to run as many things as I actually need, even though I said 4 cores were available. It only ran it on 2 anyway, right? Or hopefully it ran on 2 cores. It at least ran on 2 processes, but that's an entirely different issue. So the snow side of the parallel package. Any questions so far? Okay. The snow side of the parallel package uses sockets. I'm not prepared to call that a plus or a minus. It just is. If you're doing lots of small, quick things, sockets would be worse. If you have like a very large problem, I wouldn't expect it to really perform that much worse than an MCLApply. Works on all platforms, so this will work on Windows. And in the exercises, I mostly assume that things that are platform independent, so you can run it wherever. It's a little more fiddly than MCLApply. It's not as efficient as Forks, as I say, for like small problems. For large problems, it may not be either, but it may be. I'll show you some examples. How does it work? You create a cluster. So why? SNOW actually stands for Simple Network of Workstations, I think. It's very old. So even on your local single machine, you're thinking of creating a cluster out of those multiple cores that are really on one physical CPU. Fine. We'll call them a cluster. So we're going to make a cluster out of however many cores there are. I'm just saying detect however many. Call that thing CL. We need to keep track of it. CL tells me it's a socket cluster, 4 nodes on localhost. How nice. I can now use this different interface. So not MCLApply, it's ParSApply, ParLApply, these kinds of things. And so I can say ParSApply on my cluster 1 to 5 square root. It basically looks like an apply at that point, right? And then when I'm done, I call stop cluster on the cluster. Pretty basic. A quick summary of utilities in the package. So we have detect cores. It'll tell you how many cores are available. Split indices is like a if you need to be kind of explicit where you're sending things, that can be very useful. The multi-core side of things, there's MCLApply, MCMApply. MCParallel is pretty cool. It allows you to do almost like traditional fork join stuff, where you're not even necessarily thinking about parallel tasks. You're thinking of forking something to the background. It's really cool. It's just like you would in C or C++. In SNOW, make cluster, stop cluster, ParLApply, ParSApply, and some other things. Those are the big ones, I would say. The ForEach package. Okay, what is ForEach? It's available on CRAN from Revolution Analytics. I think it was made by Brian Lewis. Is that true? I think Brian Lewis wrote ForEach. Oh, well, I'm not remembering. I thought it was Brian. It is somebody. Somebody wrote it. The main package is ForEach, and it's like this unified interface for these different kinds of parallel interfaces for R. So like RMPI, Snow, multicore. You just want to have like one kind of syntax, and then you'll just plug in a backend like a multicore, MPI, parallel. There's a Redis, I think is how you say that. The do RNG is useful for random number generation. Snow backend. So you plug in that backend, and then the same code is going to use underneath the scenes something like MCLApply or Parallelism, something like that. So the goal is, to bind everything together, right? One ring to rule them all. Is it one ring to rule them all, or is this a horrible trick of Sauron? Let's see. It works on all platforms, assuming the backend works on that platform, right? So do parallel will use the Snow side of things, but be careful. Things like where is it? Things like do MPI will not work on Windows. I think there's still no binary for RMPI on Windows. Maybe if you build it yourself, it might work. So you can even do it in serial. It's not even necessarily something you have to do in parallel. So there's like a serial interface for this. The idea, as I say, write the code once, use your preferred backend. It's pretty nice when it works. My opinion, and this is strictly my opinion, it has a really bizarre syntax, I feel like. It almost doesn't feel like R, and I'll show you why. It also has an efficiency issue if you aren't careful, and this is well known and well documented. What is it? So this is log runtime in seconds. So I want to reiterate, this is log runtime. Okay, and this is the length of an iterating set from 10 to 1 times 10 to the 6th. The red line here is lapply, and what are we doing? Something really trivial, coin flipping. Okay, something really trivial. Then here, this is MCLApply on 24 cores, so I ran this on Nautilus, I guess. What this will do is, right up front, MCLApply is a lot more expensive than lapply. Eventually, MCLApply will start to dominate. And if I lowered the core counts, this would drop. But notice the ForEach one is going off into the stars, right? Why? Is this something that will always happen with ForEach? No. But if you do something like this, ForEach I in 1 to large number, do par, tiny thing, you will get this kind of performance. And I find this amusing because the examples in their documentation look exactly like this. So it is a good tool. You just have to be careful and be aware that in this case, what you should really be doing is chopping up the job and distributing it out into chunks to your cores, in this case 24 cores. And this shows you exactly how you would do that. If you don't, you will get some really, really nasty performance problems. So just to call your attention to it, that does exist. As long as you're aware of that, ForEach is great. But I see this kind of stuff in the wild, and you're going to tank your performance if you're not careful. So how do you use it? You load ForEach and the backend package, like do parallel. You register the backend, which is sort of like the make cluster business that we were doing before, and then you call ForEach, right? It's pretty simple. So here, library ForEach, ForEach I in 1 to 3. This is an example straight out of the documentation for ForEach. As I say, this is a simple function. This wouldn't scale well if we went in parallel, but it's a good example. Now I say percent do percent, right? In reality, this is an operator in R, just as you have like matrix multiply, that kind of operator. So it's taking. It's kind of strange how it works. I feel like it almost doesn't even feel like R to me anymore. Maybe you have a different opinion. If that doesn't bother you, it's quite nice. So we say ForEach I in 1 to 3, do, so we're not in parallel, square root I, this I here, and it will compute the it'll return a list of the square root of those values. And it will do so in serial, because I said %do %. Another slightly more substantive example here. Not sure why I chose this operation now that I look at it. I don't remember. I don't remember. It's a more substantive example. It's doing more stuff, right? This is a very simple computational example. It's not using a lot of the system's resources. This is more substantive. Why did I do that? I don't remember. But it's returning this funny thing that's trying to look at, is like the mean close to what it should be. Anyway, if we want to go parallel, all we have to do is load the back end, register the back end, and there may be some extra stuff here. This is pseudocode, okay? This is the lines 2 and 4 are pseudocode. And then change the do to a do par. And now all of a sudden you're running things in parallel. And if you want to use multi-core, you can use the do MC. If you want to use the parallel package, use do parallel. If you want to use RMPI, use do MPI. Right? You just use whatever backend that you want. So here's an example in multi-core, getting the system PID, so you can see what it's doing, what it's actually spawning. So here I say library do parallel, register do parallel, number of cores, however many that happens to be, however many I want to send, ForEach, blah, 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 do par, function. Okay? Here, for example, we're using the Snow side of the parallel package. So we make a cluster, register do parallel, pass it the cluster, and then for each do par function, stop the cluster. Okay? So how does it work? You make sure you register your backend. Different backends may have very different performance. So if we're using the multi-core side of parallel, we're using forks, that may be faster or slower than using the Snow side, probably faster. Use do par for parallel for each, and do and do par must appear on the same line as the for each call. Why is that? Because this is going to construct like a special object. And if you don't tell R that that object should do par or do something else, then it'll just print that object, right? It just won't work. It'll just print the object. It won't actually do anything in parallel. So again, I don't want to disparage you from thinking about ForEach. It's a great tool. I like to give the whole truth, like right up front. So as long as you're careful, ForEach is great. You just have to be careful. Now we're going to talk about distributed memory parallelism with R. And here's where things get a little rocky, a little wild. So why would you want to distribute? Why would you want to go to distributed computing? Because distributed computing is pretty hard. Well, nodes only hold so much RAM. We saw Nautilus had 4 terabytes of RAM, shared memory. That's a lot, but I can envision much larger data sets than would fit into memory there. Whereas we had, like 600 terabytes, not even counting the memory on the GPU on Titan, a distributed memory machine. So the amount of resources that you have available on a distributed machine are larger. And so, if you're thinking about like, within Exceed, of course, there's lots of resources available. If you fit in the Exceed ecosystem, there's Stampede, of course. Comet is coming online eventually. In April, okay. If you're outside of the Exceed ecosystem, Amazon, AWS is great. You can just pay for what you need, right? Get a couple of nodes or get one big node or whatever you need, right? But, on commodity hardware, you're staring at 32 to 64 gigabytes of RAM. If you're willing to pay more, maybe 256 gigabytes of RAM. If your problem still doesn't fit, and you're thinking also about the you want to have some like resiliency, let's say. You need to start thinking about distributing your data. So with a few exceptions, some things that I didn't talk about, FF and big memory, big analytics, R does computations exclusively in memory. There are a few exceptions, but pretty much every R package, every R function operates in memory. So if your problem doesn't fit into the memory of one node, can't use R, unless you go distributed. So there are some packages for doing distributed things. There's RMPI. Snow can use RMPI. There's, as I say, there's these Hadoop ecosystems. And there's also PBDR, which I co-develop. We'll talk a little bit about. MPI, what is it? Why would you care? It's a message passing interface. It's a way of being able to move messages and data around that high-performance network on a distributed resource to be able to solve your problem. Because you can't directly, on a distributed resource, you can't directly modify memory. If you're the program living on your part of the distributed machine and you need to modify memory over there somewhere, you can't do it directly. You have to do it indirectly. And so we can pass messages to say, either bring that memory to me, which is expensive, or here's what you should do with that memory. This is one approach. This has been the approach of the high-performance computing community for quite a while now. There used to be this thing, I think, PVM. They replaced PVM in 2001-ish. So MPI has been around for a while. It's getting better all the time. There are multiple implementations of it. OpenMPI is maybe the most common, most popular. So again, we can make these distributed machines collaborate by basically telling them to do something locally that we can't actually physically do ourselves, thinking of us as the program. So RMPI, how does RMPI work? If you're thinking interactively in RMPI, you say mpi.spawn.rslaves. It uses the older terminology of master-slave. The newer terminology is manager-worker. I think it's fine to change it. If you say mpi.spawn.rslaves with 2 slaves, 2 workers, it'll return that, you can see my host name is Wutabega. So it'll return those things. It's sort of like setting up a cluster with Snow. And now I can remotely exec. I am this rank. So notice they're ranked. 0 was the master, 1 and 2 are the slaves. I am this rank of this communicator, and it'll print out that I'm rank 1 of 3. I am rank 2 of 3. Now, something interesting here is, notice there are 3, but they're indexed from 0, right? So this is the second one in the communicator. This is the third one in the communicator. Kind of annoying, but you get used to it. And then we can MPI exit, close everything down. So how you might use this with Snow, you say make cluster type equals MPI. And assuming RMPI is available to you, you can now make cluster calls, Parallelism, whatever, Parse-apply, and you'll be using RMPI. There are some issues where you need to be very careful thinking about which machine owns what data. Distributed computing is kind of hard, and that's always sort of an issue. Here we're just keeping things kind of simple. We're not worrying about that too much. There's an RMPI tutorial. It's not that extensive, but it would show you a couple of examples, like a task pull, which is terminology that gets sort of thrown around with MPI. The RMPI manual is pretty useful. You might take a look there. But I want to talk about PDMPI, which is one of the things that I co-develop. I happen to be incredibly biased on this issue. Spoiler alert. I co-develop it. PBDMPI versus RMPI. So RMPI is interactive. PBDMPI is exclusively done in batch. This tends to be an issue for people, but I point out, there's plenty of computing in the data sciences that's either exclusively or almost exclusively batch. Hadoop kind of has a REPL, interactive REPL you can use, but it's basically batch. PDMPI is much easier to install than RMPI. It's actually even easier to install on Windows. This may or may not be possible. One of our developers uses Windows almost exclusively, so he is very considerate about Windows. It has a much simpler interface, and I can prove this. And it also integrates with our other packages, which are fairly numerous at this point. So what do I mean when I say it has a simpler interface? In RMPI, if my data x is integer type, I say MPI.allReduceX type equals 1. If my data is double, I say MPI.allReduceX type 2. PDMPI just allReduceX. Okay? That function call will do these and more. Why does that matter to you? It matters because the type of 1 is a double. Type of 2 is a double. But the type of 1 to 2, that's an integer. So these little traps in R, they're all over the place. And you can get caught not understanding the type of your data because R assumes that you don't have to know what the type of your data is. It manages all those details for you. And so we do as well. And this is just one of many examples I could give. So distributed parallelism is necessary when computations no longer fit in RAM, which is becoming an ever-present problem for people in the data science community. Several options are available. They sort of go beyond the scope of this talk, things like Hadoop. Spark is an up-and-comer. Frankly, I would not pay much attention to Hadoop. I would start looking at Spark if that's the ecosystem you're thinking about. There's also the MPI solutions. We'll talk a little bit more about those, but there's only so much we can say, right? This is a very broad overview. On the note of Spark, the developers of Spark, I think they're at Berkeley, maybe. They're actually producing like a first-class interface for R, for Spark. So that's quite nice. So just a recap, ForEach, parallel snow, multi-core, some other things. On the shared memory space, RMPI, the Hadoop stuff, PBDR on the distributed space. I want to focus on PBDR for a moment because we do some things better than any of these others. We have a whole bunch of R packages. They're available on the CRAN. We maintain source development versions on GitHub. We have stuff for implicit and explicit parallelism. And when we have methods, the syntax is identical to R, as I'll show you. So we have a demo package, Pbd Demo. This isn't even complete anymore. We have a whole bunch of other stuff. Pbd Demo, basically, assume if you have been working with R and you want to go into distributed parallelism, this will teach you how, including a 140-page textbook-style vignette to teach you how to do that. We have bindings for netcdf4 data. We have bindings for this reader called Audios, which is useful in supercomputing. We have stuff for distributed matrix algebra and statistics, including some sparse stuff. Most of it's dense, though. Profiling tools, MPI. We interface all these libraries and more. So how does it do? Pretty well. This is a benchmark that, as I hinted earlier, is another kind of benchmark. Okay? A lot of the benchmarks you tend to think about are, I have one fixed size, I'm going to throw more cores at it and see where the performance begins to degrade. That's called strong scaling. This is called weak scaling. And there's a reason why I'm looking at weak scaling, because we're going out to 24,000 cores, where the network basically degrades any possibility of strong scaling. Just the actual cost of moving any data across the network is so expensive at that point. Moving data is very expensive. So we're going to fit a linear model, y twiddle x, on about 43 megabytes of local data. We're going to do it with 500 columns, 1,000, 2,000, and just as many rows as we need to fill out the problem space. The numbers you see here are the total problem size in gigabytes. So at the end, we're at a terabyte linear model, 500 columns, finished in about 30 seconds. So we fit a linear model on a terabyte of data in about 30 seconds. And this was on an ancient machine, Kraken. So we can actually do much better on modern resources. No surprise to people who study matrix factorizations. As the number of predictors grows, the compute time itself will grow because it's just harder to do. So on a 2,000 column terabyte problem, it completed in like 115 seconds or so. Pretty nice. This is actually the code that was used. Looks a lot like R, hopefully. There are some slight differences. Instead of a matrix, I have a distributed dense DD matrix. And I'm going to generate random numbers in sort of a strange way. So it's a little different from matrices in R. This does a lot of things that R's matrix function doesn't. So I'm generating some random data, and I use lmfit to fit my linear model. Looks like R, right? Every one of those 20,000 cores is running this program and only operating on the data that they need. So the scripts, they're just R scripts. Right now, it's exclusively batch. We're writing a client server to be able to interact with these things, but it's for the moment it's batch. We can get pretend interactivity with a couple of tools that we have, but not worth spending a lot of time on. How does the distributed matrix stuff work? I don't want to give the impression that this is. Here's the impression I want to give. So, the distributed matrix stuff, we are using some of the best community codes that are available, namely MCLApply. Eventually, we're moving on to its replacement, dplasma. But if you care about if you care about performance, and you really, why are you going to all the trouble of all this parallel stuff, this distributed parallel stuff, which is harder? Why are you going to all that trouble unless it's going to be faster, right? So we are using stuff that had literally millions of dollars poured into it, and then extending it for use with R, adding some new features on top. But if you want to do matrix factorizations in the distributed world, this still does quite well. Underneath, it's using a very complicated data layout. The two-dimensional block cyclic data decomposition onto a two-dimensional grid of processors. It's a lot of words. But visually, the idea is we're chopping the data into these square blocks, and we're cycling through this processor grid here, which is also two-dimensional. The reason why they choose to do that is basically because of communication patterns for distributed linear algebra. This turns out to be beneficial. The local view looks a little confusing, maybe. It looks like this. So in R, element 2.1, so on processor rank 0, element 2.1 is right next to 5.1, because R is column major. But in the global picture, that's of course not true. In the local picture, that's true. So we're distributing pieces of the matrix in this sort of funny way. The reason you would do that is because we get really good performance when we do that. And we have hundreds of methods with identical syntax to R, assuming you're in that format. So if you want to do like bracket to drop a row or column, you don't have to think about this decomposition of the data. We already did. Oops. And so you can use bracket to drop a row or columns or do all kinds of crazy stuff. R-bind, C-bind, these are available. Linear model fitting, principal components, covariance, everything linear algebra under the sun, QR decompositions, even some simple statistics, median, mean, row sums, whatever. Like, the closer to linear algebra you are, the better Pbd Demo can do. We also have some sparse stuff for sparse matrices, matrices that are mostly zero, where you don't want to actually store the zeros. That's fairly experimental, but it exists. And the point is, if you in serial say cov x for the covariance, in distributed, why not also say cov x for the covariance? The only difference is what's x. Here it's a matrix, here it's a distributed matrix. So that's the philosophy. And here's, again, just more examples. You take the covariance, principal components, we can drop stuff. We can even use apply. We have apply, by the way. So it's pretty nice. It works really well in its domain. If you're not thinking about things like linear algebra, matrix factorization, statistics, modeling, that's the focus of the package I'm describing right now, Pbd Demo. If you're thinking more in terms of database operations, simple operations, this may be overkill. There are other approaches. But if you're thinking about, data reduction by principal components, I mean, principal components is an expensive operation. People think about it as a way to reduce the number of variables. But we ran a principal components on, it wasn't even that much data. It was like, I don't remember. Well, we ran a principal components that I felt like should have completed really fast, and it took like an hour at like 12,000 cores. Do you have 12,000 cores to throw around? So principal components is a really expensive operation. If you're thinking about data reduction, you really better just do that once and be done with it if you're going to do that kind of thing. Anyway, okay, so quick wrap up, and we're basically right on time. What? Before you do that, do you have time for 2 questions? Or do you want to do the wrap up? Let's do the wrap up, and then we'll hit the questions. And okay, so this is the model that I have been implicitly suggesting this whole time, right? Just get the thing working. Once it works, profile it as best you can. Once you know what your bottlenecks are, what are your options? Do you want to play around with LApply, vectorization? Maybe somebody else solved the problem for you in a package that they're giving away. Consider that. Look for those things. Incorporate C and C++ code or Fortran code. Go parallel, or maybe a combination of these things. What is your need for your problem? What is going to be sufficient so that you don't have to tie up your compute resources when you don't need to. Don't forget the free stuff, BLAS, bytecode compiler, the C compiler you used to build R, and then just repeat these as needed until you get the performance you want. But that's all I have before we take some questions. There's a follow-up session a week from today, 1 to 3 p.m. Eastern Time, where if you have questions, if you tried something and it didn't work, you didn't understand, whatever, I will just be around to answer questions, talk with you about whatever you want to talk about. To do so, follow these instructions. I won't harp on it. You're perfectly literate folks. So thank you so much, everybody who attended in person, everybody who attended remotely. We really, really appreciate it. We hope this was useful and enjoyable, at least most of the time. Hopefully I'm still coherent. Thank you so much. If you have any questions, I will be happy to take those now.